Well, thank you for having me. I am Irene. I'm from the Danish Meteorological Institute, so the weather service of Denmark. And today I'll be talking about all the different solar forecasting products we make at DMI and that we do research on at DMI, also within the Task 16. And I will also be talking about things that Søren and Kristen have been working on, which are my colleagues who couldn't be here today. Also, for the record, I made the slides in Danish because last year it was in Danish. Um, but I will explain in English. That is also more comfortable for me. So, we are a weather service, so we make forecasts. We make them on many different timescales. So I will go through the different timescales, and that's also the structure of the presentation. So we make forecasts of the past, we make forecasts of the future, and we make forecasts of the very near-term future. And these are the timescales we're talking about. So the past is backwards in time of years. The nearest future is minutes to hours. And when we talk about days into the future, then we are talking about numerical weather prediction, like Jakob also said. So let's start with the past. What does it mean to forecast the past? It means to basically simulate the weather of the last however many years. What we have done at DMI is we've taken a weather model. Weather models, they get improved all the time. So we've taken one, and then we've recreated 30 years of weather over Denmark and surrounding countries at a 2.5 kilometer spatial resolution with an hourly output. And this is the current temporal window, so from 1990 to 2023. Now, there was a nice question about how can we make a solar atlas? This could be the product to base it on. If we want to compare it with the most known reanalysis data set, that would be ERA 5. I don't know if you've heard about it. It's a global reanalysis. We're talking about completely different spatial scales. So ERA 5, which is made by the European Center for Medium Range Weather Forecasts, ECMWF, it has a global domain, but the spatial resolution is 31 kilometers. We have many, 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 many more years of ERA 5, but if you want to resolve clouds correctly, you need a higher resolution. So here, for example, you can see the same day, the GHI, so global horizontal radiance, from DANRA on the left and from ERA 5 on the right. And you'll already notice how different the field is. And you can see how much more variability you get in a high resolution simulation compared to a low resolution reanalysis. Yeah. I'll also just mention real quick that unfortunately it's covered by the, the bar that I was trying to remove, but DANRA is available. It's a paper on arXiv. If you Google DANRA, the Danish reanalysis, you should find it, even if you can't read the link. All the 3-hourly time steps have been made available. So if you go to the end of the paper, you'll see how to access the time steps. But global horizontal radiation is not included yet. That will come also in the kind of open data files. So if you want to monetize it, you may, I suppose. I'm not saying this on behalf of DMI, obviously, but we're providing it for free. Then we've been basically validating this data set. I'm not going to show you a bunch of figures now. However, the main conclusion is that the cloud variability is indeed much better captured in a high resolution reanalysis. You obviously need to have a reanalysis that ingests data, like real-time observations every few hours. Otherwise, you lose the whole realistic cloudscape. It's also very useful to run a reanalysis always with the same model, because obviously if you use the weather forecasts that we're providing and you try to make a statistical analysis over many years, then you'll have also improvements in the model over the years. And you don't know whether the global horizontal radiation that you're analyzing the statistics of is changing because the model is changing or because the global horizontal radiation has been changing. So it's good to have one model that you've used to simulate all the years. And the point with having a reanalysis is that besides doing statistical analyses of the past, you could also technically have information on where to place your solar farms around Denmark. And what we also work at DMI is training machine learning models to make fast forecasts, but that's for another day. So let's talk about forecasts for the future. Let's talk about hours to days, which was another question that came up in Jakob's talk. Our primary product is the numerical weather prediction product, which is what you see if you go on dmi.dk. You have to understand that a national weather service, like its main function is to use a global weather model and then nest a regional weather model, like what Jakob was really nicely explaining, and running it at higher resolutions within the global weather model. So a global weather model, the one from the European Center for Medium Range Forecasts, runs at a 9-kilometer resolution, but we all know that clouds can be much smaller than that. So you need a higher resolution weather model nested within. And that is what we do at DMI. We run a model called Harmony, and we develop it together with Ireland, the Netherlands, and Iceland. And these are our 2 domains, because we also forecast for Greenland. So the red is the Greenland domain, Iceland, Greenland, it's called IG. The blue is the Danish, Ireland, Netherlands, Iceland domain. It's at a 2-kilometer resolution. It's run every hour on a supercomputer in Iceland, and then we fetch it from here. Now, an interesting thing you can do is you can run many versions of the future, and that way you can account for the fact that weather is chaotic. So clouds kind of pop up in different places. They're often not resolved, even at a 2-kilometer resolution correctly. So a good way to kind of understand the uncertainty in your forecast is to run an ensemble, since we don't know the true forecast. So what DMI does is we run 30 ensemble members. The more members, the bigger of a supercomputer you need. So it's kind of, that's the cap. And then we run one deterministic control member. So what you can see on DMI-DK is you go from having just one line that represents temperature and wind and rain to having a spread. And that's due to the ensemble members. And here's an example of how wild it can get with these ensemble members. This is just one specific time step of a forecast in September at some random year, and it's rainfall that you're seeing. And these are all the same time step, but all the different members. And you'll notice that, I mean, in one member you might have rain over all of Jutland, and in one member Jutland might be clear from rain. So it is a bit, and I shouldn't say this as DMI, but it is a bit random because weather is random. However, this helps give you some sort of spread, and so you can understand what is the risk of something happening in certain places. So what my colleague Søren is doing for the task, he's participating in this benchmark that Jakob was describing by putting the DMI forecasts of global horizontal irradiance into the benchmark. But he's also been looking at trying to validate the ensemble and trying to see whether looking at the median or the mean of the ensemble is better than just taking one deterministic forecast. Here he was showing basically the comparison with ground-based observations. And here is the, let's say, analysis of the first few weeks of the benchmark. I'll try to make this very brief. The outcome of this analysis so far is that the ensemble mean is the best. And I can show you where to look. Let's see if this works. Nah, no. This one? No. Oh, hey. Okay. So look up here. This is the root mean square error. The smaller the error, the better. This is on the x-axis, you have the forecast lead time. And on the y-axis, you have the error. The blue line, so this is the it's the forecast lead time root mean square error for the ensemble mean. It's the lowest of all three. The red line is the ensemble median, and the black line is just one member of the ensemble, so the deterministic forecast. So this is it's a first analysis, but it shows with a spread of all the ensemble members, it shows that the ensemble mean is the best so far for the month of November. So it's quite interesting, and it's one of the first validations that we have at DMI of the actual skill of the global horizontal irradiance predictions. Okay, then I was going to talk a little bit about what Christian works on. Please do not ask me questions on this part. I am not a climate scientist. So what about the future? This was a question that came up last year and I couldn't answer because, again, I'm not a climate scientist. So it's nice that we have this part included this time. If we want to look at tens to hundreds of years into the future, what is the solar radiation expected? The best thing we can look at is how polluted is the air. Afterwards, we can talk about clouds, but in climate models, which are very coarse, we're talking about 100-kilometer grids, you can't really resolve clouds, but you can make assessments on how you expect the pollution to be. So please write to Christian for any questions. What you can look at first is historical trends. Okay, so let's see here. The top plot shows how sulfates, which are air pollutants, how they have changed in the last from 1990 to 2015. So in the last 25 years. The main point is that over Europe, they have decreased, as you might imagine. And over, say, India, they have increased. Okay, so this is just saying the air is a little bit more polluted over India. It's a little bit less polluted over Europe. Aerosols, or these kinds of pollutants, they have a negative effect on climate change. So that's the bottom plot. It's just showing the different radiative forcings. So aerosols kind of cool the earth. They shade the earth, yeah? So very simply put, when you want to run a climate model, you have to give it the forcings that you expect in the future. And there's many different scenarios that you can choose. And the newest versions of climate models, CMIP 6 and CMIP 7, they have this kind of plume model where you say, okay, there's this plume of pollution in the air that it will be this strong in this period of time. Very simply put. Okay, and then these are all the scenarios that they're running climate models with. So the top scenarios are the green scenarios of the future, and the bottom scenarios are the, let's say, fossil fuel scenarios of the future. We don't know which scenario it will actually happen because we don't know how humanity will evolve or develop or whatever. So the top scenarios, you expect that most countries, most continents, they have a strong decrease in emissions of air pollution in the future. And in the worst case scenarios, you see an increase in parts of the world. So in a very, very summarized way, if we look at the green scenarios, this air pollution will go down everywhere. So that would give the maximum solar resource in the future, not talking about clouds here, just talking about air pollution. So in Europe, we're fine. That's the takeaway, but we do not know how the clouds are evolving in the future. That's my weather perspective. yeah, climate scientists might say differently. And please contact Christian. He's been doing a really nice review of all of these papers. Now, on to my work. So I work on nowcasting, which is forecasting solar radiation in the near future. This is, let's say, oh, sorry about that. This is for the intraday market, if you want to talk about trading, but it's also for balancing the grid. And we are very lucky at DMI that we have access to real-time satellite data from the geostationary satellite called Meteosat second generation and third generation. The one we're currently using, it scans all of Europe, all of Africa, every 15 minutes, and you can see the clouds. This is an example of the very simple algorithm that we're using. You take in a sequence of images from the most recent ones you have access to. Here's an example of 45 minutes from now, 30 minutes, 15, and 0 minutes from now. So this would be the real time. And then you predict the future images. So this is pure computer vision. There's no numerical weather prediction model involved. This can run on your laptop in like 3 seconds. It's simply taking the cloud objects and moving them with the motion vectors that you extract from the past sequence of images. But it works pretty well. If you want to validate it, you can look at what actually happened. And here, for example, you might want to know when this cloud will pass over Jylland and you'll have clear sky in Jylland. It's not perfect, but if you want to look at single locations, you can take, for example, locations across Denmark, and then you can see how much was the global horizontal irradiance in the past. So those are the yellow dots. And then what do the different models that we're trying predict? We're also running ensembles by adding noise to the images. Here are just 2 examples of models that we're trying to use. And then you can look at that and you can think, okay, maybe the second figure, this alludes, the medians allude to the fact that there will be a ramp down in Samsø, and then maybe a ramp up. So you can actually look at what actually happened. Those are the green dots. And you can see there was indeed a ramp down and a ramp up. Then if you look at the location close to Copenhagen, the medians say that it's going to be pretty stably cloudy. However, the spread in one of the models would allude to the fact that there will be an increase in solar radiation later on. And if we run the model again an hour later, and we can keep running this all the time, that's the nice thing about such a light model, then you can see that both models, both medians of ensembles, predict the ramp up quite nicely. So just a very quick explanation of nowcasting. There's some more things we have to work on because there's a new satellite now. It's a 10-minute resolution and has a higher spatial resolution. But especially now in Eginet, our TSO is going to, well, we've gotten a very nice agreement with them to work on this for 3 years. So you'll be hearing much more about this if we have this nice arrangement next year. And we will be delivering it as an operational product on free data, so not monetized, this was part of the agreement. Very nice. So that is it from me. You're welcome to reach out. You can actually see the emails, they're not covered. And again, Søren and Christian will be happy to also answer any questions. Thank you.